So we were discussing more about the harmonic wave last time, and we saw the general equation of the harmonic transverse one-dimensional wave. So transverse one-dimensional sinusoidal or harmonic wave. We saw the general equation is A sine omega t, okay, plus minus kx plus phi, okay, where as usual A is the amplitude, so maximum displacement from mean position, omega is 2 pi f for angular frequency, k is 2 pi by lambda or what we call angular wave number, and the wave speed is omega by k or f lambda. Okay. And we also saw last time that the average power propagating through the wave is half mu v omega square e square. Okay. And then of course about this relationship v is equal to f lambda, we saw that the propagation speed v is square root t by mu, so it's a medium property. F is the property of the source, okay, and therefore lambda, which becomes v by f, is affected by both the medium and the source. Okay. And accordingly, the power also adjusts itself. So you can see that the power being half square root t mu into omega square e square, or half mu v omega square e square. So in this formula of power, it is basically the power propagating through the wave which is the same thing as the power supplied by the source. So the power supplied by a source in that sense is the source's property, but it contains properties of the medium, frequency, so that is something of the source, and amplitude is the thing which self-adjusts. So कहने का मतलब that suppose the source is capable of supplying so much power at a frequency of so much, but I change the medium property, like I increase the tension in the string, or I replace the string with a heavier string, so mu is greater or lesser or whatever, then accordingly the amplitude is the quantity which will self-adjust so that this relation holds. Okay, so that is something that we need to keep in mind in terms of how what affects each other. Yes, so that's okay. You can ask me the questions later. So this week I will also be sending you some extra questions on waves apart from the IIT Hub booklet. So I'll send you a couple of PDFs of DPP kind of things. So you can try out those questions and discuss those questions over WhatsApp with me, preferably over the week. Okay, before we come to the next lecture, that is next week. Before that, only if you discuss the doubts or whatever hints you require in those questions, then next lecture will also be more efficient. Okay. So anyway, coming back, so these are some of the things that we've discussed: the properties of the wave, and especially understanding which property is affected by what, medium versus the source, and things like that. Okay. And we had also seen a sort of experimental way to understand or analysis of experimental way of understanding this general equation, where we saw that if on a string you create a harmonic source, which is just doing SHM at one end of the string with an amplitude A and an angular frequency omega. So what it makes every particle in the string do SHM like that, but the phase starts varying with X like that. So you can so that was one thing, and of course we saw a snapshot picture and Y is the function of time for a fixed value of X, and we saw those interpretations, and those things are important. Okay. Now let's do some typical type of questions based on this. So for example, if we have something like this where we have a heavy rope which is suspended vertically. Now, this is a very typical type of question, especially at the JEE mains level and all. So we have a heavy gauge rope which is just hanging under its own weight. So this is a rope of mass m and length L, uniformly distributed mass. Now what we do is, at t equal to 0, a pulse is created at the lower end. So now as time progresses, that pulse is kind of traveling along the string like this. At some time t it is like this. At t equal to 0 it was at the end. So single pulse is created. So we have to find the speed of the pulse as a function of its vertical displacement y. So the pulse has traveled through a vertical displacement of y, and at that instant its speed is v. You find that out. And secondly, the time taken for the pulse to reach the top. Yes, that's correct. Just got some answer that seemed to be correct. Yeah, Ganesh, that's correct. Okay, so this is basically just a mechanics question. There's nothing much of waves in this. You just have to understand how this the tension varies with the vertical coordinate. Yes, Ganesh, that's correct. You have to just do a simple integration once you get the v as a function of x. So good, that's okay. So यहाँ पे क्या करना है? We have to just first of all find the tension as the function of the vertical coordinate. So if we have a point at which, sorry, so let us say now we are considering any point which is at a vertical coordinate y. So at this point, if you make a free body diagram of this section of the rope, which is below, and it has a mass which is y by L times the total mass. So the tension at this point, let's say this point is P. So the tension at that point is the weight of that section. So it is linear function of length. Okay. So the tension as a function of y is a linear function of this thing. So that means the pulse which will be traveling along this, when it reaches this position, the linear velocity of the pulse will be square root of tension as a function of y divided by linear mass density. So that is nothing but m by L g y. So it is y not x divided by linear mass density, which is m by L. So this, the first part, the speed as a function of y is becoming square root g into y, where g is acceleration due to gravity. Okay. Yes, so Ashish, that's correct, and Ganesh, that's correct. Okay. Then secondly, you have to see that as the pulse is traveling, the speed is nothing but dy by dt, the vertically upward velocity. So that is root dy. So integrate this. So dy upon root y is square root of g dt. Integrate this from 0 to whatever time, as your y coordinate is changing from 0 to L. So that's it now. It's very simple. So this is 2 times root y going from 0 to L is square root g into. So your time just is 2 times square root L by. Okay. This is a standard kind of situation. You should almost know this like a definition kind of thing. Yeah, I mean, you don't need to memorize the formula, but you should know the process so that you can do something like this very fast. Why I'm saying something like this is because you won't always get a question where the value is exactly this. You can also get a question where a rope aisa hai. Suppose the rope's mass is m, and you also have a weight hanging over here, and that is some, let's say, 5m or something like this. So in this you can see the tension is different. Here the tension as a function of y will become 5m plus m by L into y at a distance y. So when you do that integration, it will have a slightly different term. Okay, so it's not that just because it's a heavy rope it has to have that kind of velocity. But the important thing is that whenever you have a heavy rope, the tension is varying with position. So that means the pulse is traveling at a non-uniform speed. So hope this is clear to all of you. Yeah, you can be asked to find the average velocity here. That will become total distance divided by total time. So that's correct. Okay, so if you are asked to find the average velocity as the pulse is moving, it will be total distance divided by total time. And notice here, this will not be like a linear or like an arithmetic mean of initial and final, because it's not a linear function of time. Okay. Now moving on. Next, we will first of all remind ourselves of one important concept that we saw last time, which was the delocalization of energy. So energy propagation along a wave or a pulse. So when we look at pulse, we understand that as the pulse is like this at some time t, okay, and a very short time later, the pulse is going to become like this. Okay. So you can see that these particles right now are having downward velocity, and these particles right now are having upward velocity. Okay. And the particles at the peak are more or less at rest. Okay. Whereas these are having maximum kinetic energy. These are having maximum kinetic energy. Now also in terms of stress, you will see that this part of the thread is under maximum stress. This part of the thread is under maximum stress because there is maximum stretch over there. Because we saw that the slope of the thread being maximum. So same for these kind of pulse. So you can see all the energy of the pulse is contained in the same region. Okay. So that's how the energy is propagating along this direction with the speed v. So now all the kinetic and potential energy of these particles is shifting to this next set of particles here. All the kinetic energy of these particles and the potential energy is shifting like this along this direction. So that is what is happening in the case of the pulse. And as this set of particles will come down and reach this kind of position, they've lost their energy. But some other set of particles have gained that energy. Okay. And like that. Okay. So similarly, when you take the case of a traveling wave, continuous or periodic kind of wave. Okay. So at some instant, if the snapshot picture of the wave is like this. Now next instant, because the wave is traveling like this, the next instant it's going to become something like this. So again, you can see that these particles are on their way down. These particles are on their way up. These particles are on their way down. These particles are on their way up. Okay. And also you can see that again, this stretch is maximum over here. So again, it is the particles which are in the region where they are going through the mean position. They have maximum kinetic energy plus potential energy. Whereas it's the particles which have reached near the peaks, this set of particles, they are having tending to zero energy. Okay. And in quarter of a time period, what will happen? These particles would have all come down here. So by then, their energy has shifted. So this energy from here has shifted here. This energy from here has shifted here. And now these particles are having zero energy. So that is how energy is continuously shifting along the periodic wave. Okay. So this concept also becomes important in another context. So we'll discuss that. So this continuous delocalization and shifting of energy also becomes important when we consider this next thing, reflection of a pulse at the boundary of a medium. Okay. So since we are talking about one-dimensional transverse waves, the medium I'm talking about is basically the boundary of the medium we are talking about is at some end of the thread. End of the thread or rope through which that is traveling. Okay. So the first type of situation we'll consider is reflection at a rigid boundary. So what is a rigid boundary? A rigid boundary is one where the point attached at the boundary will have zero displacement. So it is rigidly fixed. So it cannot move. So that kind of situation. So if we observe something like this, that there's a pulse along a string, and that string is attached to a fixed end like this. So one interesting thing we'll see that such a pulse, when it reflects and comes back, it always comes back with inverted phase. What we see is when it reflects and comes back, it comes back with, so the reflection or the reflected pulse in this case is phase inverted. Okay. So there's more to the analysis than just this phase inversion, but first just make a note of this, that whenever we have a rigid boundary, a pulse when it is reflected will have a phase inversion. If we assume that there is zero dissipation of energy, then it will have the same amplitude and the same shape. Okay, so actually, technically speaking, we should make this slightly more symmetric. Okay, let me try again. So the shape of the pulse will be the same as what it was, but it will be like a mirror image. So it will be like a mirror image. So it has the same width and the same height, let's say capital E, this one, as this. Okay. So assuming zero dissipation of energy, this is what will happen. Okay, so the reflected pulse in this case is phase inverted, but it has same but inverted geometry. So just make a note of this heading and this first case. Okay, then we'll discuss more about it. Now, obviously, the thing we want to understand is how is this phase inversion created? And while the phase inversion is created, what is happening to the energy of the pulse and how the shape of the pulse is actually transforming, or you can say how it is morphing, from one shape where the amplitude is on the positive side to the other shape where the inverted shape where the amplitude comes to the negative side. So as this morphing is happening, how exactly it transforms from this to this, and during that time, how the interaction with the boundary happens and what kind of energy exchange with the boundary happens. That's the next thing we want to understand. So just make a note of this, we'll come to that. Okay, so something very interesting about how this shape morphing happens. Okay. Let's come to that next. So what we observe is like this, that as this pulse comes nearer to the boundary, something like this first happens. So the first thing we observe is that the amplitude remains the same, but this width, it sort of becomes less than this. In fact, the symmetry goes. You can see that the shape of the pulse is changing from this to, as it comes nearer to the boundary, it's shifting to something where the left half is the same, but the right half becomes smaller. So it changes to something like this. So it's like this side is remaining W by 2, but this is becoming less than W by 2. Okay, so this is symmetric. Now here in this diagram, this is W by 2, but this is becoming a value which is smaller. This is some delta X which is less than W by 2. So first the width reduces. Okay. Next, what we observe in the next, you can say, screenshot, what we observe is that the size of the pulse also decreases. Okay. So now both A and W are compressed. But all this while you can also see that the peak point is moving closer, still moving closer. Okay. It's still moving closer to the boundary. And eventually there is one snapshot when this happens. And then the same thing appears in reverse. Now there's a small peak that appears. That peak morphs into something larger, but with asymmetry. So again, this is back to the original amplitude. This is back to the proper half width. But this is less than the half width. And then eventually, we have this shape there. It's the same width as the original pulse, the same amplitude. So we'll understand in detail how this happens also, and what happens to the energy of the pulse as it is morphing. We'll understand that also. But first, make a note of this series of these diagrams, or at least understand it. Okay. This is explained in somewhat detail in Resnick-Halliday. Okay. It's not explained in HCV and all so much, but it's explained in Resnick-Halliday. Okay, now if you want to understand why this situation is occurring, you have to understand how it interacts the pulse and the medium. Does the first half stays same amplitude while the other half tends to 0? No, actually, I'll explain. So you'll understand geometrically, it doesn't exactly happen like that. Before this peak reaches the wall, actually, this amplitude will start decreasing. Okay. So I'll explain. In a diagram, you'll understand how this happens in the next series of diagrams. But before that, let us understand how, okay, this is exactly happening in terms of impulse. So what is happening is that the boundary point on the wall, let's say the boundary point is this point. The boundary point on the wall, as the pulse reaches it, no, it continuously applies a downward impulse and doesn't allow the string. So what is happening is, as this pulse is traveling, is the energy of this pulse which is pulling these points upwards, and the string here doesn't have too much resistance to offer, so these points readily go up, and that's how the energy that is contained here is now shifting here. The energy that is contained here is shifting here. But as the boundary of the pulse reaches the wall, now what is happening? This tries to make this move upwards. Okay, but as this applies an impulse, the wall's boundary point applies a downward impulse like this. So it doesn't allow this point to move. Okay, and as a result of that, what is happening is that gradually there's a shift of energy. So let's understand how that shift of energy is happening. So right now you can see that in this diagram, this region and this region, they contain kinetic energy plus potential energy. Okay. Now, if you come to this diagram, or for example, if you come to this diagram, you can see that there is less potential energy compared to this. The amount of stretch is less. Okay, but the rate at which these points are coming down, it's faster now. So there is more kinetic energy and less potential energy compared to this diagram. Okay. And now compare this to this. Here, what is happening? While the string has become like this, but you can see these points are very rapidly going down. So in the next diagram, that their position has changed from positive side to negative side. So this is now converted to pure kinetic energy. So all the time as you're going from here to here, what is happening? Kinetic energy is converting to potential energy till you reach this situation where kinetic energy becomes maximum, potential energy becomes zero. That is when the string looks like its displacement is zero for an instant. And then again you can see that it is now from here to here, again kinetic energy is converting to potential energy. And we have here again a mix of kinetic and potential energy. There's a mix of kinetic energy plus potential energy. So in terms of energy, this is what is happening in that morphing. This is what is happening in the transformation. Okay. So that's another thing conceptually you should understand, that the interaction with the boundary is such that the impulse that the boundary keeps applying, or the continuous kind of force that applies over the time for which this pulse interacts with the boundary, during that time the impulse does this. It converts potential to kinetic initially, and then again the wave on the basis, the medium on the basis of its momentum, it tends to stretch downwards. So again, as it stretches downwards, the internal conservative forces, you're doing work against them. So part of that kinetic is again converted to potential energy. Okay. So you'll also understand that it's basically like this boundary point is applying a very sharp sort of jerk in the downward direction. Imagine you did not have the incoming wave, but you are just you just had a string which was like this, and next moment you see that okay, there's a pulse traveling in this direction. So what would your conclusion be? Your conclusion would be कि इस point पे, boundary point ने किसी ने downward ऐसा sharp jerk दिया that is creating the pulse. So that's the same thing that's happening here also. But it's happening in such a way that the jerk is provided at a time when this forward coming pulse was interacting with that boundary. So it cancels that forward pulse and creates a downward pulse. That is the role that the end point at the boundary plays in this reflection. Okay. So now there's a good way to understand the geometry of the wave as it shifts. So to understand the transformation of the incident pulse into the reflected pulse, okay, which is phase inverted. Okay. what is happening is at the boundary point, there is a sharp downward impulse, okay, that acts in such a way, acts such that the boundary point has zero displacement. That particular point of the string that is attached to the boundary, that has zero displacement. And that is what creates, and it creates a phase inverted pulse. Okay. So this whole situation, so this interaction between the incident pulse and the boundary point or the boundary impulse as it interacts can be modeled, okay, as the following. It can be modeled as the interaction of one pulse on a string with another pulse which is traveling like this. The same amplitude, same width. Now if you take sort of the midpoint of these two, this distance is equal to this distance and they are traveling with the same speed. Now you'll see that this point behaves in the same way. So the point P will actually behave the same as the two symmetric pulses overlap at the point. So as they overlap, what will happen is that let's say this is pulse 1 and this is pulse 2. So you'll always see that the net displacement at an overlap point will be the displacement due to pulse 1 plus the displacement due to pulse 2. Okay, so this is the net transverse displacement at a point of overlap where they overlap. Okay, so this thing, this wide net at the point P, which is the symmetry point, will always be 0. Okay, that we can understand geometrically, and that is why it behaves like a rigid boundary for the incoming pulse. For pulse 1, it behaves like that. Okay, so now let's just for a moment imagine this. Okay, so what we are saying is that the actual situation we have is that there is a rigid boundary here. Okay, but we are modeling this thing with an imaginary mirror image pulse like this. So this side of the system is imaginary. This is the actual real part of the system. So what will happen now? Let's understand what happens when they overlap. So as they tend to overlap, now let's say now we are going into the imaginary part. So this is here. Okay. And at that point of time, my imaginary pulse traveling like this would be something here. So what is the actual superposition of these two? So what is the superposition of these two going to look like? So to understand the superposition of these two, let's look at this situation. This like this, and you have this like this. Okay. And this is where your boundary is present. So you'll see that just at the boundary point, क्या होगा? इसका जो positive है और इसका जो negative है, वो एक दूसरे को cancel कर रहे हैं. So the addition of this y coordinate with this y coordinate with respect to 0, you'll see will be something like this. The resultant displacement, यहाँ तक it is the single wave only. Okay. But from somewhere here, it is the addition of this with this negative one. So it starts sharply decreasing. And it starts sharply decreasing such that it becomes like this. And then that again continues. It becomes like this. That continues till some point here. So this is what the superposition would have looked like. Okay. So in our actual case, where the boundary wall is present, and this is just a diagram to, this is just an imaginary wave added over here. So what will happen is at the boundary, you can see that this is happening. That is why this has become less than W by 2. But this is W by 2. And this is still, because it's actually the superposition of this black line and this blue one. You can see that exactly at the boundary point over here, at the boundary point P, the positive displacement of this forward pulse and the negative displacement of this reverse pulse are cancelling each other. Okay. So two smooth curves interacting, this is how this diagram will look. Okay. So that is what happens when this pulse comes against this. That's why first is the width that starts getting squashed slightly. Okay. Now next diagram, so let's say this was our picture 1. Okay. Now our picture 2, it's come even closer. Okay. So now in the second picture, let's say the wall is somewhere here. So the forward pulse is like this. Just a moment, guys. All right, so let's just look at this whole thing once more.
Right again.
So let's say this is our forward pulse, and now this is our reverse pulse going like this. The forward pulse is going like this. So the midpoint of these two things is somewhere here. So that is where our wall is present. So now you can see that even the peak is getting squashed. So when I draw the superposition of these two, what is happening is up to somewhere here, the resultant is unaffected by this. But after this, it doesn't go up so sharply because there's a negative value here. So this becomes like this. So you can see what has happened now. The actual shape of the medium has become like this. So this amplitude, this delta y has also become less than P. And obviously this whole delta x is less than W. So that's how the shape of the medium has changed. So it goes from this kind of shape to first something like this, where the amplitude is the same, but on one side the half width has reduced. Then gradually the amplitude also starts decreasing because this kind of overlap happens. Okay? And as this overlap continues, there will be a stage when you can take a third diagram where both the forward and the reverse pulses are present at the same position. So they are exactly overlapping each other. Because both the peaks have reached the position where the boundary is present, or the symmetry point between them. So this is where the boundary is present. So here they will just cancel each other. And then next picture, what will happen is that the reverse pulse is now actually crossed over to some point like this. So now the boundary is somewhere here. So you can see that the superposition of these two now will create a shape which is like this. And then eventually boundary is somewhere here. Okay, so then it creates a shape where this reaches the full amplitude, but this is less than the half width, and this is W/2. And then the next picture like that. Okay, so this is the way to physically model exactly how the shape moves. This one, Sudhir. Okay. Something has gone wrong with this note. Okay. I think the lines have got. So the interaction of the incident pulse with the boundary point P, that can be modeled as the interaction of two symmetric pulses below 1 and 2 interacting at the symmetry point below. So this thing, this is how we can. And the reason we can do that is because the point P will actually behave just the same as the boundary point. Just like the rigid boundary point P would have behaved. Because the displacement at such a point would be 0. That's what happens over here. The superposition of 1 and 2 creates. No, right now we are talking about a single pulse. So, it's like as the pulse hits the boundary point creates a jerk downwards. So, if a continuous series of pulses with a fixed time period hits the wall, the wall keeps creating downward jerks with the same continuous time period. So, the wall actually acts like a simple harmonic oscillator, which is creating downward impulses. So, it will create inverted pulses with the same time period. So, if you have a series of pulses which are upward phase, downward phase, upward phase, downward phase. So as these hit the wall applies impulse which is opposite. So as a downward phase, this thing pulse hits this, it creates an upward jerk. As the next one creates, it creates a downward. So yeah, the wall basically creates a simple. So the reflected wave will also be harmonic. If the incident wave is harmonic, the reflected wave will also be harmonic. So we'll come to that next. Okay, when we understand the reflection of a periodic or continuous wave at a rigid boundary. But here we are looking at a single pulse and we're trying to understand how it will morph its shape as it is coming back. So this series of diagrams is what we need to understand properly here. Okay. So here, as this is just about coming to a position like this from here, it's just about coming to a position where if the wall had not been there, it would have gone like this. So what actually happens, that is over here. Okay. The next, as it comes to a situation where the peak is even closer to the wall. So if the wall had not been there, it would have gone past this wall at a point like this. So what happens in that case? That's then the lower diagram. Okay, so just understand this. You don't need to note this down in detail. It's there in resting clarity also. Plus, we will do an actual problem based on this. Then this is the shape where the pulse has reached a position where if the wall had not been there, it's exactly like this. And then this is like, you can see a fourth diagram, this is a fifth diagram. Okay, so there have been instances of interesting questions in JEE Advanced based on this kind of idea. So let's look at one. So let's imagine we have a triangular pulse. So that's why I said we have to imagine, because a triangular pulse is physically not possible, because you cannot have corner points like this. The string shape will always have a differentiable kind of curve. But if we imagine that we have a triangular pulse like this, such that this is 3 centimeters, this is 3 centimeters, and this vertical height is 4 centimeters. And this is traveling at the speed of, let us say, 20 centimeters per second. And there is a rigid wall present over here, such that this distance is some, in fact, let's make this slower. Let's make this 10 centimeters per second. And let us say that this distance is 20 centimeters. So draw the shape and calculate the width and height of the pulse at, so this is the snapshot picture at t equal to 0. This is the snapshot picture at t equal to 0, whereas we want to calculate the width and height and also draw the shape at t equal to 2.1 seconds, t equal to 2.2 seconds, t equal to 2.3 seconds, 2.4 seconds. Seconds. So this is a triangular pulse, transverse 1D, travels along a string and reflects back from a rigid boundary. Assume zero energy dissipation. So assuming zero energy dissipation, okay, so the only way you can understand the shape exactly how it is changing is by modeling this situation as a superposition with an imaginary pulse coming from the other side, which is inverted in phase and traveling in the opposite direction. So you have to do that imaginary superposition with like a mirror image pulse of this symmetrically coming from the other side. Okay, so just try this out. It's a very interesting type of problem. But just the thing is that you have to understand that this is physically not exactly possible. If it was physical situation, then instead of a triangular pulse, that would be more like a curved kind of pulse where you don't have sharp corner points. But this is just for the sake of calculation, so that we are able to do the calculation easily. We are imagining something like a triangular pulse. Yeah, Ganesh, I will just verify your answers. Yes, 2.1 and 2.3. Yeah, they're correct. Yeah, your answers are all correct, Ganesh. Now, the shape is something that is interesting. So, basically, you will see that at 2.1 seconds, it's like some point over here has reached the boundary, which is. So, if we draw the shape at 2.1 seconds, now let me try and draw an exact kind of shape. So, 3 by 4. So, अगर forward pulse ऐसा है, this is the forward pulse. Then at 2.1 seconds, the boundary is somewhere here. So the reverse pulse, you will see that imaginary reverse pulse would be like this. So now it's like a graph thing. You want to superimpose these two. So the superposition of these two, let's say I'm drawing with a stronger line like this now. So you will see that this is the same. And up to here also is the same. But then, similarly, here it would be the same. Here it would be the same. But in this region, it would become like this. If you were to actually write the equation of the lines and superimpose. So this is the superposition. And just to show, okay, so actually, how will the shape of the string be looking at this instant? The shape of the string will be looking like that half part. want to draw an exact figure, it will be something like this. So this is the boundary point, and this is how this is looking at 2.1 seconds. The peak is still traveling towards the boundary, and you can see that this semi width is same, but this has changed to 2 centimeters. So the overall width has changed to exactly. Now you have to add these two lines, then you will understand it. If you write an equation of this line and an equation for this line, y equal to mx plus c kind of line, with this point as the origin, you will see that at origin that displacement will be 0, but here it adds such that the slope changes. It's just mathematics, basically. So you can see how the shape of the string is changing. The shape of the string at the original time was like this, and from this. So in the picture before this, the shape of the string was something like this. So you can see how the shape has changed from here to here. So it has changed from that shape to this shape. Okay. Now if you see at 2.2 seconds, let's say this is the forward pulse. And the reverse pulse now, or before that, let's look at the boundary line. So the boundary line is now here. Because the forward pulse has gone 2 centimeters beyond the boundary line. So it has gone 2 centimeters beyond. The peak is 1 centimeter from it. So each of these boxes is 1 centimeter. So now your reverse pulse is at this instant going to look like this. So it's a different kind of superposition, as you can see. Alright, so now the superposition of these two, if I am making with the thicker red line, so that's like this here, like this up to here. Now it has a very interesting shape in this region. क्या हो रहा है? यहाँ से लेके peak तक ना, it will flatten out like this. Okay. And then from here to here, passing through this. No, up to the peak again, sir. So here it will be like this. Then again, so it will be something like this. This will be the shape. So you'll see, because it has flattened now, the height has changed. So this height will be 2/3 of this. So it will be 2/3 of the peak. So 2.67 centimeters. That will be this. Okay. Whereas this is 2, and this is also. So the actual shape of the string, you will see, will be like this. Just a moment, I will reshare this to restart the whiteboard program. All that you'll understand from equation of line and similar triangles and all that over there. Similar triangles से आपको समझ में आ जाएगा. उसका height 2/3 क्यों है? Just follow my cursor. I'll explain. Just a minute. So how I'm getting that height as 2/3 of the full height? Just follow my cursor. See this triangle, this smaller one. Getting it? ये वाला triangle और ये वाला triangle, this larger one, जिसका peak 4 centimeters है. They are similar. Okay. So this larger triangle has a base of 3. The smaller triangle has a base of 2. So they are in 2/3 ratio. So the height is also 2/3 of 4. Okay. So just I want to make things easier for myself. So I'll try to cut paste this diagram. See if it works. Yes, it works. Okay. So now to get the exact shape of the medium at this instant, I will remove all the supporting lines and just stick to this one. Okay. So this is what actually the medium will look like. this is going to be the shape of the pulse. And if you compare it with the earlier diagram, you'll understand how the progression is happening. So the shape is changing from this to this to this. .2 seconds. So now let me draw up a proper comparison of all these things. Just give me a second, guys. So to get a proper comparison of all these shapes. Oh, sorry, this was not required. Anyway. Okay, so this is the progression of events now. Okay, this is the progression of events. This is how the shape of the pulse is changing. And then you will see that at t equal to at t equal to 2.3 seconds, they would have completely overlapped. So it will look like this. It's pure kinetic energy. And at t equal to 2.8 seconds, it will again be back to the original shape, but with inverted phase. So these are the shapes that I'm getting. So guys, hope this is clear to all of you. Bhumik, is it clear? Height कितना आ रहा है, कैसे आ रहा है? 2.1 सेकंड पे. Okay, good. हाँ, 2.2 is a bit unique. Na? The shape only changes. The peak gets squashed. It's no longer a sharp point. That's also an interesting feature. So in real life situation, it will not be like this because it's not a triangular curve. It's not a triangular shape. These are more curved. So it's you won't have so many sharp corners. But again, the situation is more or less something similar to this in a curved function context rather than in a geometrical shape with sharp corners. So you just curve out the corners a little bit, make them a little bit more curved at the corners. You will see how the curvature is changing as you go from shape to shape. You understand how the curvature is changing. So anyway, I think one revision of this at home when you are going through the notes and should be enough. Okay, booming. So it's clear right now, right? So the values are clear to all of you, I hope, okay, of the peaks and everything. Okay. Now moving on, there is another kind of situation for reflection at a boundary. So let's come to that now. So this was our first case of reflection at a boundary. The second case is reflection of a pulse at a soft boundary. At a so-called soft, or what we understand as flexible boundary point. So this is the type of boundary point. It does not offer any resistance. Does not offer any resistive impulse to transverse displacement. So it's the sort of boundary where you're trying to yank or trying to shift that boundary point in the transverse direction. And the boundary point, unlike the rigid boundary, which completely resists with a sort of a transverse impulse to resist any type of transverse displacement, ये क्या उसका opposite है. It's completely flexible. So you're trying to create a transverse displacement through an incident pulse, and the boundary point will not resist it by applying any kind of impulse at all. It's completely flexible to movement in the direction. Okay? So the physical model of this is this, that you have at one end of the string, you have a smooth pole. So this is a rigid, fixed but smooth pole. And you have a ring going around this. So this is a ring that can slip freely on the pole. Okay, and your string is tied to it. And your thread is tied to it. Some kind of incident pulse, which has again some width and some height. So here we'll see it's actually the opposite. Here what happens is the reflected pulse will come back in phase. So what we'll observe is that after some time, the reflected pulse will come back in phase. It will just be moving like a mirror image. Rest it will be the same shape. So the reflection occurs without phase inversion. So just make a note of this first, then we'll come to the exact progression of the shape morphing, how it happens. Okay, so now to understand the shape thing in more detail, you'll understand that here the reflection at the flexible boundary can be modeled as the superposition of pulses 1 and 2 as below. So we have this pulse, and this is, let's say, so-called boundary point. We have this pulse 2, same width, same amplitude. So you will understand here that what happens is, as the forward pulse, let's say, comes to a position like this. Now suppose the boundary is here, right? So So the mirror image pulse that we are imagining will be something like this. So the superposition effect here will be something like this. The superposition of these two. Now see, from this point onwards, it's a positive quantity plus a positive quantity. With respect to this, you can see it's a sum of two positive quantities with respect to this position. So the resultant, which I'm drawing with the dotted red line, becomes like this. यहाँ पे double हो जाता है इसका. So the shape of the pulse changes to this kind of shape. Like this. This half width is the same. This amplitude is the same, but now this delta x is less than the half width. And it's become like this. Then by the time there's more overlap, by the time the peaks have come closer, now you can see that the boundary will be like this over here. So the overlap now is looking something like this. Looking something like this. Okay. So at this point of time, the shape of the string has changed to this. So this delta y has become greater than that amplitude. And then eventually when they exactly overlap, the superposition actually looks like this. The amplitude doubles. So that point of time, the width exactly halves and the amplitude doubles. And then it comes back this kind of shape. Then it comes back to this kind of shape. And then it eventually comes back to this kind of shape. All this time, this pulse peak is traveling in this sort of direction. So the progression of the wave pulse this time happens like this. Oh, sorry. This is after the 2 wave picture. So it's now starting to travel like this. Up to this point, It's traveling up now. So here also in terms of energy, the opposite is happening to what we saw earlier. Ganesh, the model is of two equivalent waves because there is no loss of energy, and because it's like, here if two waves like this superimpose, then the displacement of the symmetry point would be maximum. Whereas if it was an inverted pulse wave 2, then the displacement of the symmetry point would be 0. So in the case where the displacement of the symmetry point is maximum, it corresponds to a flexible boundary, because a flexible boundary allows for maximum displacement. And a case where the symmetry point is having 0 displacement as a result of superposition, it corresponds to a rigid boundary point, because the rigid boundary point would be so Sudhir, in the case of a membrane, you have basically like the skin of a drum, like if you take a snare drum, it has a sort of disc-shaped kind of membrane which can vibrate. So they actually produce two-dimensional waves which reflect back from the boundaries, and these reflections create something called standing waves. So the standing waves in the skin of a drum or a tympanium or something like that creates a type of function called a Bessel function, and that creates certain kind of harmonic or modal waves. We'll be discussing about harmonics and modes later, but we will always discuss in context of one-dimensional medium rather than two-dimensional medium, because two-dimensional medium requires more complicated mathematics. On a two-dimensional medium, you will have to take your horizontal coordinates as the xy plane and the vertical as your z-axis. So for example, if a horizontal two-dimensional medium is in vibration, then your z will be a function of x, y and time. So that is a more complex kind of waveform, which we will not be getting into because of our mathematical this thing, limitations at this stage. So that's why we limit ourselves in mathematics or mathematical form of mechanical waves only to one-dimensional waves. In fact, that is done at a later stage in graduate physics. If you take a course in graduation physics level, it's not necessary. In engineering also you will be studying two-dimensional waves or three-dimensional waves in that much detail. So also you can see here the combination of kinetic energy and potential energy from here to here as you're going. Kinetic energy is converting to potential. So here it's a combination of kinetic and potential energy. Right now the pulse is not yet reached here. So it's a combination of kinetic energy plus potential. But compare that with this, it's still kinetic and potential, but the kinetic energy in comparison to this has decreased. The potential energy has increased because the shape is changing like that. So by the time we reach this picture, where this has become 2A, the kinetic energy has become 0, because all particles are momentarily at extreme position, at their highest point. Okay, and potential energy is maximum. And from this picture onwards, again, potential converts to kinetic because there's a lot of stretch. So the internal conservative forces, they pull the string down and convert part of this potential energy into kinetic energy. So now we have again kinetic plus potential. Okay, again kinetic plus potential. So, but kinetic energy is now increasing, potential energy is decreasing. So potential energy is converting to kinetic. So for conceptual, objective questions, multiple choice types, this is also important to understand that as the pulse interacts with the rigid boundary converts your potential energy to kinetic energy. And when the pulse is right at the rigid boundary, making the net displacement 0, then it is converted to pure kinetic energy. The energy of the pulse is in the form of pure kinetic energy for just that instant. And then again, as it reflects back in inverted phase, kinetic energy converts to potential. But in the case of flexible boundary, it's the other way around. The boundary doesn't apply any impulse at all. So as a result of that, your kinetic is converting to more and more potential because the string is stretching more and more as no resistance is offered. So when the peak reaches the symmetry point in the peak reaches the boundary, so the boundary's displacement becomes twice of the original amplitude of the peak. That is when your string is having maximum stretch. So all the particles have reached the extreme position. So your potential energy is maximum, but momentarily kinetic energy is zero. Then again, the elastic forces within the string, nothing to do with the boundary, but the elastic forces within the string are reconverting that potential energy into kinetic energy. And as a result of that interaction of energy again, your pulse is reflecting back. Okay, so hope this is clear. So in one case, the rigid boundary is applying like a downward jerk when the pulse there is trying to create an upward motion. So that is what is converting your potential to kinetic and causing it to flatten out and then again reflect back with inverted phase. Whereas in this case, the boundary is not offering any jerk at all. It's not offering any resistance. It's just causing the energy to get reflected back. So that can be modeled as the interaction with a symmetric pulse which has the same phase, not phase inversion, what we've done over here. So this is quite a complex part in the understanding of waves, though the type of questions is very limited. Like I showed you that type of question. The next one also has a couple of questions where there is continuous reflection happening between two boundaries, rigid and soft, and try out those questions, you'll understand what to do. So now from this situation, we come to a situation where a continuous wave might be having this kind of interaction. So next example, we'll see a continuous wave or a periodic wave. So in our example, we'll take a one-dimensional harmonic transverse wave. Okay. Reflecting, okay, and also transmitting to a boundary point. So we will understand this through the example. So we have this situation. Now this is a junction point between a heavier gauge string and a lighter gauge string. This is the junction between a heavier gauge string, say mu2, and let's say mu1. Okay. Now this is going up to infinity, and this is also minus infinity. Okay. So from x tending to minus infinity on the lighter thread, an incident wave a harmonic wave y equal to e naught sine omega t minus kx is incident on the junction where, let us say, the tension is 25 or let's say 250 newtons. Mu1 is 1 gram per centimeter and mu2 is 4 gram per centimeter, and the incident wave has frequency equal to let's say 50 hertz and amplitude equal to 1.8 millimeters. Okay. So we want to find the amplitudes, wavelengths, speeds, that is propagation speeds, and frequencies of the transmitted wave, that is transmitted through the junction. Yes, that's correct. Okay. Onto heavier stream, and reflected wave, that is reflected from the junction onto the lighter thread. Okay, so just understand the question first and just take down the data of the question, then I'll start explaining how to solve. Yes, Ganesh, that is correct. Frequency will be common. Okay, so we will let's understand this step by step. First of all, let's do whatever calculations we can at this stage. Okay. So we can see that the incident wave's amplitude is 1.8 millimeters. That was given to us. Then the incident wave's velocity, B incident, let's say, is square root T by mu1. So that is square root of 250 divided by 0.1. So that is 50 meters per second. And omega, which is 2 pi f, will become 100 pi radians per second. So lambda for the incident wave, frequency will be common, so I'm not labeling frequency as incident or reflected. So lambda of the incident wave will be uh, V incident upon F. So 50 divided by 50. So 1 meter. Frequency was 50 hertz. This omega by K. So K is equal to omega by V. Sorry, 2 pi. Pi by 2, but 2 pi radians per meter. Okay. So this is the property of the incident wave. Okay, now the thing is that we will have to treat the boundary point, because the junction point is the boundary between a heavier medium and a lighter medium. We'll have to treat it as a rigid boundary. So the assumption here will be that my junction point will have to be treated like a rigid boundary. No, because the medium is heavier on that side, so it offers resistance. So it's like, see, the incident wave is coming from the lighter side. Okay, so the incident wave that is coming like this incident wave, it's trying to move the junction point. So let me take the junction point as x equal to 0, suppose. So the incident wave was like this. It was E naught sine omega t minus kx, let's say, where omega was 2 pi f, k was 2 pi upon lambda incident, okay, and E naught was this thing. Okay. Now what is happening is at x equal to 0, what kind of displacement the incident wave is creating? It is creating a displacement of E naught sine omega t. Whereas the boundary point will, now the string on this side is heavier compared to this side. So every time a pulse like this comes here, this offers resistance. So it will act like the rigid boundary. Every time a pulse with a negative phase comes in, this offers resistance. So it will reflect back with positive. Okay? So because the medium on opposite side of the junction has more inertia, that is, your mu2 is greater than mu1. Okay. So the junction point, which we are taking as x equal to 0, acts like a, this thing, what we call it, like a rigid boundary. Okay. So reflected pulses will have phase inversion. So therefore, a reflected wave or series of pulses, periodic pulses, you can say, so they are like periodically generated pulses. Okay. Has phase inversion. So at x equal to 0 minus, that is left hand limit of the junction, just to the left of the junction, which is x equal to 0, if the incident wave at x tending to 0 minus is creating pulses like this, okay, the reflected will create pulses which are like this. Let's say A1 sine omega t plus phi. So these are reflected pulses or the wave with an amplitude of A1, frequency of f only of 50 hertz, but phase inverted. So my reflected wave will become A1 sine omega t plus kx plus pi. This is the reflected wave. Equation. Okay, so just write down up to here, then we'll talk about the transmitted wave. Then we'll see how to calculate the amplitudes. So just one thing here, the reflected wave propagates through the light stream, which is in the x less than 0 region. Okay, so that's why lambda of reflected wave is equal to lambda of incident wave, which is 1 meter. Okay. K of reflected wave is equal to k of incident wave, which is 2 pi radians per meter. And obviously, therefore, velocity of reflected wave is also the same as the velocity of incident wave. It's 50 meters per second. The reflected wave has this velocity, this wavelength, this k, and obviously frequency is the same as the incident one. So this incident wave is creating a reflected wave in this, along with the incident. Why does it have? Because there's transmission also happening. So there will be conservation of power, assuming no dissipation. So the power of the incident wave is going to be distributed between the power of the reflected wave, and also there will be a transmitted wave. So there will also be a transmitted wave. That's why the amplitude will be different. Okay, understood, na Ganesh? Instead of the junction point being of a heavier string, if the junction point was fixed to a wall, then there is no transmitted wave. Then obviously you're correct, that your reflected wave will have the same amplitude, assuming zero dissipation of energy. But here, the energy of the incident wave or the power of the incident wave is going to get distributed between some amount of power reflected back and some amount of power transmitted. Understood, na beta? Okay. So that is one of the equations we will have to actually incorporate, okay, to get the this thing. So to get the value of amplitudes, we'll actually have to incorporate power conservation. So just take a look at all these points first. Then we'll come to the transmitted wave also. So far, based on the equation of the incident wave, we have written some kind of an equation for the reflected wave, where we don't know the amplitude of the reflected wave, but we know the phase and we know the frequency and the wavelength. Okay, so this will become the equation of the reflected wave, where if you put the limit x tending to 0 minus, obviously you get this equation. So that's the reason why the amplitude is different, because the power of the incident wave is not just equal to the power of the reflected wave. It is distributed between transmitted wave and reflected wave. That's why they will have different amplitudes. So now we are coming to the transmitted situation. Okay, so also in the region x greater than 0, that is on the heavier string, a transmitted wave okay, operates or propagates along positive x-axis. So that transmitted wave has an equation, let's say, of E2 sine. It will have the same omega, but some different key. Okay. So what will happen here is that, why I'm not writing any phase difference phi here, is that this side x tending to 0 plus will be E2 sine omega t, which should be in same phase as incident wave, because the transmission does not involve any phase inversion. Okay, at that point, the incident wave at that point x equal to 0 minus is creating E naught sine omega t. So it should be in same phase and of course same frequency. Okay, so therefore same omega. But since the medium x greater than 0 wala medium has different mu, okay, mu2 equal to 4 gram per centimeter. Therefore, both the speed of propagation and the lambda, they are different compared to incident and reflected waves. Okay, so coming back to the transmitted wave, it has some amplitude E2 sine omega t minus k prime x. It's traveling in the positive x direction, so the sign is minus. So here omega will be 2 pi f, so that is 100 pi radians per second. But the speed of the transmitted wave will be square root of t by mu2. So that will change. That will change by a factor of half. So this will be 25 meters per second instead of 50 meters per second. and therefore the lambda will become 25 divided by 50, so 0.5 meters, and therefore your k prime will become 4 pi radians per meter. So now the only thing remaining is A1 and A2. So now the only thing we have to calculate is A1 and A2. And for that we have to write two equations. Now one equation I have given you a hint will come from power conservation. But the second equation is something very interesting which we will discuss. Okay. So just note down this first, or just go through these points. No, gram per cc beta is 10 raised power minus 3 divided by gram per centimeter. Okay. 4 gram per centimeter is 4 into 10 raised power minus 3 divided by 10 raised power minus 2. Sorry, kilogram per meter minus 3. So as you get used to doing waves questions, you will get used to this, that gram per centimeter converted to SI unit, there's a factor of 0.1 that you multiply. Remember, it's linear mass density and not density. So okay, so now the next two things to calculate A1 and A2 you'll see is something like this, that the power incident at the junction will be equal to the sum of the power reflected plus the power transmitted, assuming no dissipation of energy. So now we just apply the formula. So half square root of P into mu1 into omega square into A naught square is equal to half square root P into mu1 again, omega square A1 square plus half square root P into mu2 into omega square E2 square. Now you know that your mu2 is twice of mu1. Sorry, mu2 is 4 times mu1. So this equation will just convert to A naught square is equal to A1 square plus 2A2 square in this particular case, because of this. So this is my equation 1. Now remember, we have to generate a second equation because both the amplitudes A1 and A2 are unknown. So the second equation comes from a very interesting logic. Okay. The second equation comes from this logic that in the region X negative, that is the lighter string of linear mass density mu1, okay, the net disturbance at a point is the superposition of the incident wave and the reflected wave. It is the superposition of the displacement due to incident and reflected waves. Whereas in the region x greater than 0, that is the heaviest string, mu2, the net displacement at any point is just the displacement because of the transmitted wave. Now, the string at the junction x equal to 0 is intact. We are assuming it does not break. So if there is no break in the string, so that means y as a function of xp should be continuous at the junction. Because the string should not break. Okay. So that means we'll apply the equation of continuity at x equal to 0. Y at x equal to 0 minus should be equal to y at x equal to 0 plus. That is, left hand limit should be equal to right hand limit of displacement at the junction. Okay. So basically this will be what? This will now become y incident plus y reflected at limit x tending to 0 minus should be equal to y transmitted at limit x tending to 0 plus. Okay. So just write this equation and see what you get. So that will give you your second equation. And then solving A1 and A2 from the two equations will give us the answer. Okay. So just understand this point and then try to populate that term that I've written for continuity of that point with a proper equation, substituting the values. Okay, so because the string is continuous at that point, it doesn't have a break. So mathematically, at any instant, if we draw the snapshot picture, at any instant of time t, the displacement on the left hand limit should be equal to the displacement on the right hand limit. Okay. So basically substitute this. So the incident wave had an equation of E naught sine omega t minus kx. Okay. The reflected wave had an equation with phase inversion, and also direction is inverted. Just give me a moment, guys. I'll reshare. Okay. So the reflected wave had an amplitude of A1, omega same, k same, but direction reverse, and also phase inversion pi. Okay, so this thing at limit 0 minus should be equal to the transmitted wave's equation at limit 0 plus. So the transmitted wave was E2 sine omega t minus k prime x, but no phase term because it's in phase with the incident wave. So this now put the limit, so it will become E naught sine omega t plus E1 sine omega t plus pi. So that's actually minus E1 sine omega t. This should be equal to on that side. So you can say that at any instant of time, A naught sine omega t minus A1 sine omega t must be equal to A sine omega. So A naught minus A1 is equal to A. That's our second equation, and our first equation was A naught square was equal to A1 square plus 2A2 square. Okay, so now solving these, we'll get the amplitudes. Okay. So we get here that E naught square is equal to E1 square plus E2 can be written as, or let's just substitute E1. It's easier that way. So E1 will be substituted as E naught minus E2. It's a very simple equation actually. So plus 2A2 square. So we get that 3A2 square minus 2A naught A2 will become 0. So obviously A2 can't be 0. So the only possible solution we have is that A2 is equal to 2 by 3 A naught, and E1 is equal to E naught by 3. So finally, these are giving me the amplitudes, and the other things like transmission speed and wavelength and all that we already found out earlier. So this is one important JEE advanced type of application concept and analysis, which is like the extension of the concept of reflection at a boundary. This is not exactly like a reflection at a boundary. It is more like a reflection from a junction point where combination of reflection and transmission is happening. You can also see that one more solution of this quadratic term is that E2 is 0 and E1 would become equal to E0. But that solution would occur in a place where there's no transmission occurring. So instead of the second string and all that, you have a rigid wall only at the junction point. In that case, there would be no transmitted wave. So there would be no transmitted amplitude of power. So that would give you that case. But Okay, people, so hope this is clear fully. Yes, if it had been heavier to lighter, then the reflected wave would be in the same phase. So if mu1 had been greater than mu2, then that phase inversion term pi would not have been there. So then our second equation, the one for continuity, it would have given us something different. It would have given us that A naught plus A1 is equal to A2 instead of A naught minus A1 is equal to A2. Okay, so people hope this is clear. So with this we conclude the fourth lecture of waves, and now you can solve everything in waves up to the point where there is interference or superposition of two waves in the same string, or the case of standing waves also, which we'll be discussing in the next lecture. Okay. So I will send you a couple of DBB kind of problem sets, plus you can do questions from HC Verma and from the exercises in your module, which I've also sent separately in your group. Okay, so that's it for today's class, people. Okay, wish you all the best. And also don't forget to review your Sunday's test paper. Okay, and if you have any this thing, okay, I will send you a list of questions you can do from the module. Yeah, so don't forget to review your Sunday's test, and especially if you have anything pending from geometrical optics from that, make sure you do that. There was also a practice paper for JEE mains level which was posted on the website. So please get hold of that, or otherwise ask me for it on this thing. So there are some questions on geometrical optics in that practice paper which you can try on.